All right, everybody, we are going to look at some pedigrees. Pedigrees are all about tracing certain traits through the generations. Now, there's a couple things that we should know, and for the most part, it always uses shaded or non-shaded and squares and circles. So again, we're talking about traits. So if something is shaded, it means it has the trait. If it is non-shaded, it means it does not have the trait. And when we look at squares and circles, squares typically represent males and circles typically represent females. Now, as we go through this, um, it's just analysis types of things because a lot of times we know if someone has a genetic disease in a family tree, but we are trying to figure out how that is traced through the generations. So again, we get back to our lovely Punnett squares. And, we have a little pedigree like this. We can track who has it, who doesn't have it. And based off of this, we can try and assume what their Punnett square would be like. So let's get right in. First one we're going to look at is autosomal dominant traits. So these are not traits that are linked to genes on X chromosomes. So these are linked to these genes are on any of the other autosomes. So when we're thinking about autosomal, we are not thinking about the X's and the Y's, we're just thinking about the trait itself. When we're thinking about autosomal dominant, if something is dominant, again, the shaded would have the trait. And if this is a dominant pedigree, the shaded having the trait could either be big A, or heterozygous, big A, small a. And the non-shaded does not. So non-shaded are small a, small a. So using that information, can we answer some of these questions? We have these different generations here. What is the genotype of 2, 3? So 2, 3 does not have the trait. The only way you do not have the trait is if you are small a, small a. So what is the genotype of 3, 1? 3, 1 has the trait. And again, when we're talking autosomal, male and female really does not matter at this point. So 3, 1 right here, we know it has it, but that doesn't necessarily tell us whether it is big A, or big A, little a. So what we actually need to do is track back to the parents. And these parents here, one has the trait and one does not have the trait. Again, when we're thinking that does not have the trait here, this we are thinking has to be AA. So this mom could either pass this A or this A, but regardless, it's going to get a small a. So when we're talking genotype here, again, that's the letters. What is the genotype of this one? It can't be that, it has to be this. So we are looking at a heterozygous individual. All right. So as we keep going here, we're doing the same type of thing. Is 1, 1 homozygous dominant or heterozygous? 1, 1's right here. Is it homozygous dominant or is it heterozygous? So if we're thinking about this, go back to Mendel with his P generation. If this were a P generation and this is that, if this were a true breeding, capital A, all of the offspring would be heterozygous. And all of the offspring would then have to have the trait. Is that the case? So that son has the trait. Now again, this one is not part of this generation because it doesn't come down. So this has the trait, this does not. This has it, not, has it. Since there are some here that do not have the trait, the only way it cannot have the trait is if it's little a, and therefore this dad is heterozygous. So, moving right along. Okay, autosomal recessive. In autosomal recessives, again, we're not messing with any of the X's yet. We're only focusing on the A's. Shaded has the trait when we are talking about recessive traits. So now anything that's shaded is going to be little a, and that is what we know for sure. Again, there's some things that we know for sure and some things that we don't. Non-shaded now could be this or this. This is a little bit, we're getting more along those lines of thinking about um, recessive diseases now, okay? Things that show up rarely. So at this point, this has the trait, okay? Now, if we keep on going, AA is a carrier, so it can skip generations. So these could have it, could have the allele, even though they're not displaying the trait. So unshaded parents that have shaded children must be AA and heterozygous carriers. This right here is going to come into play when we aren't told what the pedigree is and we're trying to figure out what is the pedigree, but we're not there yet. So number one, what is the genotype of 2-3? 2-3 right here, again, it's a male, so don't get into the X's and Y's yet because we're not there yet. All we're thinking about are the A's. So it has the trait, therefore it's AA. 2-1 right here does not have the trait. Therefore, it could be either of these, and we need to try and figure out which one it is. Is it a carrier or is it homozygous? So, how can we figure that out? From here, we can look downstream. Okay? So, neither of these have the trait, but they have children that have the trait. If they're going to have children that have the trait, can they be homozygous dominant? Can they be this? Because absolutely not. Could one of them be that? No. The only way these children get both small letters is if both of the parents are carriers, because then they can pass on the little a's to their offspring. So that is the answer for 2-1. 2-1, they're that. What's the probability that 2-1 and 2-2 would have a fifth child with this trait? So now we know what 2-1 and 2-2 is. What is the probability that they are going to show up with little a, little a? And again, now this comes back to Punnett square business. What is the probability of having the trait? And it is to have the trait, they have to be homozygous recessive. So that is 1 out of 4. That's the probability of having another child that's also having it. So they're kind of beating the odds right here by having 2 that already have it. Okay, let's move on. All right, this is a little bit bigger, but that's okay. We're getting into X-linked now. Again, when we start thinking X-linked, now we are putting the traits on the X chromosomes. And this is different because we start introducing the Ys for the males. So when it's X-linked dominant, it's going to be shown with females that are homozygous dominant or heterozygous. The only way a male has this trait is if they have the X allele for it. So non-shaded does not have the trait. So if they're non-shaded and they're a female, they have to be homozygous recessive. If they're a male and do not have the trait, have the recessive allele. Okay, so as we go here, if we start trying to figure out some of these genotypes, we have what we know, and then we need to try and match it up with the pedigree. 1, 2, right here. What's the genotype of 1, 2? It's a female, and the only way a female does not have the trait is if it is homozygous recessive. What is the genotype of 2, 5? So right here, 2, 5, it does not have the trait. The only way a male does not have the trait is if they are recessive on their X allele. Okay, so now could 2, 1 and 4, 4 have a son with this trait? So as we're looking at this, 2, 1, we're looking at right here, and 4, 4 right here. Could they have a son with this trait? First of all, again, it's kind of asking us to do a Punnett square. In order to figure this out, we need to take a look at what are the genotypes of both of these. So 2, 1, this dad has to be that. And 4, 4, this female could be X capital A, X capital A, or X capital A, X small a. And how in the world do we figure that out? Well, if we trace this back up here, we find out that this mother does not have the trait. Therefore, this mother is X small a, X small a. So one of this child's X's has to be X small a. So, and this dad having it has to be, okay, sorry, this dad is X small a, XY, or sorry, X small a, Y. This mom does not have it. So she is XA, XA. Oh, I'm sorry. So yeah, this dad is right here. Brain's a little slow this morning. So what we're looking at is that these are mixed up. This female has it. Therefore, she got the dominant trait from her dad, and she has one dominant A from dad, and we'll display that, and got one small a from mom. So we are looking at this like so. When we Punnett square, we want to figure out if the sons will have the trait. Is it possible? And according to this, it is because right here, this son with its Y would have the trait. Okay, let's keep rolling. Okay, so moving right along here. We are looking at X-linked recessives now. And one of the things that should jump out at you when you see this pedigree right off the bat is how rare you see some of these things and how really rare you see um, women that have this. Because the only way they can have it is if they carry both recessive alleles on their X chromosome. So again, that's pretty rare. Um, the males that have it, as you can see here, are going to be XAY. All of these non-shadeds do not have the trait. Um, the you can have carriers, but males cannot be carriers. And the only way a daughter can have it is if their father has it. So if we're going to answer these questions real quick here, what is the genotype of 3-2? So 3-2. Again, coming back here, it has to be small a, y. What is the genotype of 2-2? Right here. It's non-shaded, it does not have the trait, it's a female. We can narrow it down to these two right here. Okay, now which is it? So again, the only way a male can have the trait is if it gets a recessive allele from its mom, because it can't get that X from dad because it's only getting the Y from dad. So therefore, this mom has to have that, but if she had two of those, she would have it. So since she does not show the trait, her other X has to be capital A. So that genotype there is going to be heterozygous. The next question says, could 2, 1 and 2, 2 have a daughter with this trait? Is it possible from this situation to produce a daughter that is XA, XA? And the answer is no. The only way a daughter can possibly get it is if the father has it. Because this dad we know does not have it. The only thing he can pass on is not having it. And therefore, this girl can never have this genotype. And therefore, it can never have the trait. All right. Now, it gets a little tricky when they don't tell you what the pedigree is, but you need to try and figure it out. They don't tell you who has the trait, who doesn't have the trait, but I mean, it does tell you that whether they have it or they don't have it, but with this, it's a little bit tricky because you got to try and decipher it. So is there anyone, the first question, if you're just given a pedigree, the first question you should ask yourself, and again, this is a quick way to do it, there are some little loopholes, but is there anyone in the phenotype, anyone whose phenotype is different from both of their parents? So the first thing your eye should scan for is two parents that have the same phenotype. This doesn't work, this doesn't work, this does work. So your eyes are drawn to two parents that have the same physical presentation of the trait. And then what we're trying to figure out, if is there anyone who's, and if the pedigree doesn't have any that are both unshaded or both shaded, now you're kind of in a little bit of limbo. But neither one of these have it. So then we want to know, do they have any children that are different from them? So is there anyone with a phenotype different from both of their parents? And there are, because these two right here do not have the same phenotype as their parents. And now from that, we can try and figure out whether it's recessive or whether it's dominant. And if neither of these have it, but yet they can pass it on to their offspring, what that means is that they have to be carriers for this. And if they are carriers for the trait, that makes them heterozygous, and that makes their children that have it homozygous recessive. So if you have two unshaded, but you end up with shaded offspring, that is a recessive pedigree. Okay, so you got a recessive pedigree, but now is it X-linked recessive or is it autosomal recessive? And to figure out if it's X-linked recessive, there are a couple rules that we need to look at. And because it's X-linked, we're going to focus on the girls. Are there any girls with the recessive phenotype who have a father or a son with the dominant phenotype? All right, let's see if we can figure what the heck that means. So we've got girls, and if they are recessive, again, they're the recessive. If they're recessive, they have to be X small a, X small a. So if they are X small a, X small a, their father must have it, because the only way you can be X small a here is if your dad passes you an X small a. If this were X large a, like in this one, it is impossible to have a female that has the trait. So first of all, if there are any females that have the trait whose dads do not, it is not X-linked recessive. Same things along those lines. If there are any females that have it, they are this, right? Therefore, their sons must have the trait as well. It is impossible for a son to not have the trait if their mom has the X-linked recessive trait. So we are looking for anything that might break these rules. A daughter not having a father that has it, or a mom not having a son that has it. And if any of those rules get broken, then it's autosomal recessive. So first of all, let's find the girls that have um, the recessive phenotype. And we know this pedigree is recessive already because of this situation right here. So who are the girls with the recessive phenotype? It's this one and this one. Okay. Now, do they have any sons? Again, it's impossible if it's X-linked for a female that has it to not have a male. And right here, this one right here does not have it. And then just to have more evidence right here, this father does not have it. Therefore, this pedigree is not X-linked recessive, but it is autosomal recessive. Okay, so now that's how you kind of figure out what type of pedigree it is. Now let's kind of look at an actual AP question here. Okay, so the following figure displays data collected while studying a family, some members of which have sickle cell disease, a rare genetic disorder caused by a mutation in the hemoglobin beta gene. There are at least two alleles of the HBB gene. The HBA allele encodes wild-type hemoglobin, and the HBS allele encodes the sickle cell form of hemoglobin. Genetic testing provides insight into the inheritance pattern for sickle cell disease. Figure 1. It's a pedigree of a family with affected individuals. Squares represent males, circles represent females. Shaded symbols represent individuals with sickle cell disease. Did it tell you what is the inheritance pattern of this? It did tell you that um, that males or that shaded represents with sickle cell. So as far as sickle cell goes, part of it, you might already know this inheritance pattern just because you remember some of the other things we talked about with sickle cell, that it's on the 11th chromosome, and if it's on the 11th chromosome, it's automatically autosomal. And the only way you end up with sickle cell is if you are homozygous recessive. Okay, but using our little clues here, let's see if we can figure this out. Is it dominant or is it recessive? We know that shaded represents people with sickle cell. And the first question we would ask, are there any children who have different phenotypes than both of their parents? So immediately when you start looking at a pedigree, try to find parents with the same phenotypes. And that exists right here. Okay, so parents have the same phenotype and there is an offspring with a different phenotype. If they have the same phenotype and produce an offspring that's different from them, the only way that can happen is if they are carrying the allele. So the only way it's not displayed in these um, individuals is if they are carriers for it and their normal hemoglobin is what would be displayed and they don't have the disease. So that immediately tells you that they have it and these are carriers. When you hear carriers, you're thinking heterozygous. So that automatically puts us in this world of recessive. So now, is it X-linked or is it autosomal? And again, some of the rules, if the females that have it, they their male sons must have it and their fathers must have it, which is not the case in this situation. So this will tell you that sickle cell is not X-linked, it's autosomal linked, which we already knew because it's on the 11th chromosome. So as far as this goes, what is the inheritance pattern? It is autosomal recessive. And we already can pick out some genotypes here. If they have it, they have to be all of these that have it are little a, little a. All right, so let's go and check out the questions. So again, this is the same sickle cell pedigree, and these are the questions here. Based on the data shown in Figure 1, which of the following best describes the genotypes of individual family members in the pedigree? So again, genotypes, we are thinking these types of letters, but in the little thing they were talking about, these letters are represented with HBS or HBA for wild type. And that's a capital letter. This S is basically representing the small a. So let's see here. Let's see if we can narrow down the choices. All affected individuals possess at least one dominant allele of the hemoglobin beta gene. And affected individuals, based off of what we understand about the pedigree, and basically what we understand about sickle cell in the first place, is that they have to have both of the mutant alleles. So healthy individuals may be then, so this is not right. B, healthy individuals may possess one mutant allele of the hemoglobin beta gene. And because this is recessive, again, it could be that. Okay, so P is definitely in our world of being right. C, individuals 4 and 5 must be heterozygous for the mutant allele. Okay, 4 and 5 both have it. So are they heterozygous? And the answer is no. If they have it, they have to be homozygous, recessive. So D, individuals 2 and 6 possess 2 copies of the wild type, the healthy allele. And is that true? Well, if they are that, then they are definitely passing on a healthy one to their children, and those would all be carriers and none would have it. So again, this cannot be true, and B is the correct answer. So this last question here will be all finished up. Possessing a single copy of the HBS sickle cell allele has been shown to provide some resistance to infection by Plasmodium falciparum, the parasite that causes malaria. Which of the following individuals represented in the pedigree would have the greatest selective advantage in an area where malaria is common? So, possessing a single copy. So what they're asking for are what individuals in this pedigree would be big A, little a. So is number 1 big A, little a? No. Is number 2? We just kind of answered that before. And again, if that's that, maybe yeah. Um, this 2, maybe I answered that, I messed up on that last one. Okay, so 2 actually, in order to produce at least one child that is not affected. Sorry. All right, so I'm good here. Um, as we look at this, um, so this situation, um, again, this has to be a carrier because it's producing some individuals that have it. Okay, if 2 was homozygous, all of its offspring would be heterozygous and not have sickle cell. So 2 we think is right. Let's check out 3. So 3, there's a chance possibly that it could be because It's not out of the world of possibilities here that that could be a carrier. We don't know for sure. So 3 isn't absolutely wrong, but right now 2 is better. Okay. And then 5, it has it, so it's not this. And that makes B our best answer, even though C isn't necessarily wrong either. So, all right, that's pedigrees and how they're applied on AP types of questions.